All right, so this is a follow-up video for section 6.1 on slope fields and differential equations that is for BC calculus students only. So this is going to cover a concept that is only required for the BC calculus exam, not for the AB calculus exam, and that is Euler's method. So the slide that you can see here are simply the steps that you go through in using Euler's method to find a solution to an initial value problem. And you can read through that yourself, but I'm just going to jump right into a problem. So example 5 here says to let f be the function that satisfies dy dx equals x plus y and f of 2 equals 0. Use Euler's method and increments of delta x equals 0.2 to approximate f of 3. So the whole purpose of Euler's method is the concept of a tangent line basically mimicking the actual function for x values that are very close to the point of tangency. This is particularly helpful when we have a differential equation such as x plus y, where we could not algebraically work backwards to figure out the function that it came from. If I could figure out the function that dy dx equals x plus y came from, then I could just do my antiderivative, find my plus c, and then substitute 3 into my function. But I can't do that. So instead we use Euler's method. So when I'm doing Euler's method, I basically organize everything in a table. So I have x, y, delta x, delta y, and x plus delta x, y plus delta y. So those are my 5 columns. So to begin with, you start at the point that you know. So they told me that when x is 2, y is 0. So delta x, that represents our change in x. It is the same as saying dx like we're used to. They gave us that value as well. It is 0.2. Delta y represents dy. They kind of gave us that. What I have up here from the differential equation that they gave me, let's scroll down, I have dy dx equals x plus y. But that does not say dy equals. So what I have to do is take the dx and multiply it to the other side. So that tells me that up here in my table, delta y is equal to x plus y dx. And then the fourth column I'll explain when we get to that. So what I'm going to do is I'm going to move in small increments, so in this case in increments of 0.2 in the x direction, and basically create a new tangent line there with a new slope there. But at the moment, if I move x by 0.2 units, then I'll move y by x plus y times dx. So that means that the y is going to change by 0.4 units. So the new point that I'm at, I was at 2, but it is changing by 0.2. I was at 0, but it is changing by 0.4. So my new point would be located at 2.2, 0.4. And I'm going to repeat this process for each new xy pair until I come to an x value of 3. So my change in x is going to be constant. It's always that amount of 0.2. The change in y, though, depends on my current xy values and my change in x. So 2.2 plus 0.4 times 0.2. So that would be 0.52. So now 2.4, I'm adding 0.2 to it, and 0.4, I'm adding 0.52 to it. So now my point, oh, that should be a 2.2, sorry. So now my point is 2.4, 0.92. Again, change in x is 0.2, change in y is 2.4 plus 0.92 times 0.2. So that would be 0.664. So my x coordinate is 2.4 plus 0.2, and my y coordinate is 0.92 plus 0.664. And this gets tedious. Luckily, it's a pretty simplistic process if you understand it, but yeah, it's going to take a little while. And obviously, you would need a calculator to do it, at least for this particular one. Sometimes the decimals are not so bad, but this would require a calculator. All right, so the next time my change in y is 0.8368. And these are going to end up being decimals a good bit along the way. You know, in calculus, we tend to round to 3 decimals, but I would encourage on these that you go to 4 decimal places just because of how much we're going to be rounding throughout the process. So now we're at 2.8, and the y coordinate is 2.4208. Change in x is 0.2. Change in y is going to be 1.0442. And so this last time, when I change my x, I get a 3 for my x value, and I get 3.465 for my y value. So since I reached the x value that I want, I'm done. I don't have to fill in the rest of that row. And f of 3 would be equal to 3.465. So that's essentially a tangent line approximation using teeny tiny little tangents all the way from 2 to 3. All right, so the next question is pretty similar. We've got a new differential equation, dy dx equals 2x minus y. It says, and if y equals 3 when x equals 2, so we would be starting for x equals 2, use Euler's method with 5 equal steps to approximate y when x equals 1.5. So here's the thing. On the last problem, they told us what steps to take. They said make delta x be 0.2. On here, all they told us was that they want 5 equal steps. But we need to figure out how wide those steps need to be. So we're starting at an x value of 2 and ending at an x value of 1.5. So your change in x is going to be the end minus the beginning divided by however many steps they wanted you to take. So negative 0.5 divided by 5. So your delta x is going to be negative 0.1. So now I want you to pause the video and I want you to try to set up the table and work it out 100% by yourself to see if you can find f of 1.5 for this differential equation. All right, so compare my work to yours, and my final answer is down there in pink. The 2.611, not f of 3, that should say f of 1.5. Should be approximately 2.611. And yes, they will pay attention to decimal accuracy. So if you're a little bit off from me, go back and look at where you may have had a rounding issue. That wraps up Euler's method.